Okay, so why is this letter H an interesting PFD problem? Good question. You're going to see in a moment. So if I factor the denominator completely over the set of integers, I'm going to get x squared, and then the other factor is x minus 9. Well, what's so weird about that? Here's what's weird. That's interesting. X squared can be treated one of two ways. And it's up to you how you want to treat it. But once you pick which way you're going to be treating it, you have to stay in that lane. Okay? So I'm going to give you both choices, and then I'm going to tell you which is my personal favorite. But you don't have to use my favorite. I mean, as long as you use one of the choices, you'll still end up in the same boat, the same answer. So this x minus 9 is clearly a linear factor. But x squared you can think of one of two ways. One way you can think of it is you can think of it as the quantity x minus 0 getting squared, which means you can treat it as a repeated linear factor. That's one way to treat it. I can't write today. The alternate way of treating this x squared guy is you can treat it as a single irreducible quadratic factor. Well, which way is better? That's not really the question that you can be asking. It's really the question is which way do you feel more comfortable treating it? Because ultimately we're still going to end up having to get the same number of unknowns, and we're going to end up with the same final result. So that's it. So let me just go over both ways of treating it. If you decided that you like way number 1, yeah, I can see how that's a repeated linear factor. Yeah, that makes sense to me. Then the integrand, when you break it up into partial fractions, will look like this. So number 1, your 81 over x squared x minus 9 becomes a over x, that's for the first factor, plus b over x squared, that's the repeated, plus c over x minus 9. And go get your basic equation and go do what you need to do, okay? The other way of treating this, and this is, you know, just an alternate way, is to say your 81 over x squared x minus 9 is going to become, if you're treating this as a single irreducible quadratic factor, you'll have the x squared down there. And then remember, irreducible quadratic factors get a linear factor as its numerator, not just a pure number all by itself. And then you'll still have another partial fraction for the linear factor x minus 9. So either one of those will work, but you have to pick one, okay? So you see that you still need to get 3 unknowns? And then if you choose this way, once you get your A and your B, you're going to then have to use the split up trick. And then after you use the split up trick, I claim you're going to end up with these 2 fractions here anyway. So you're going to end up in the same boat. So it's kind of like up to you which way you want to roll. When you hit the show an example button on My Math Lab, I don't know which one they're going to send you to. So I want to show you both just so you don't get confused and, you know, whatever. But you have choices here. So it's up to you. I'll use way number 1 just because. Okay, so if I use way number 1, and then I clear fractions by multiplying both sides by the LCD, which happens to be that original denominator, x squared x minus 9, my basic equation then becomes 81 is equal to, after reducing, I'll have ax, the quantity x minus 9, plus b times x minus 9, plus cx squared. So there's my basic equation, and that's the equation that's going to help me get the unknowns a, b, and c. Whoa, okay. Well, I hope you guys can see that if I plug in x equals 9 into my basic equation, it'll kill off the first two terms and I'll be able to figure out what the unknown c is. Let's do it. Let x equal 9. Cool. So then I'll have 81 is equal to, well, this is going to go to 0, this is going to go to 0, but I'll have c times 9 squared. But that's 81, and if I solve for c and divide both sides by 81, I get c is 1. Cool. That works. Now it's kind of up to you. Do you want to do the equate coefficients technique? It's one of my personal favorites. So let's do it. Let's do the equate coefficients technique. This is a review from Wednesday. So if you weren't here Wednesday, this is going to be kind of confusing, but here's the deal. You multiply everything out on the right-hand side, distribute and all that stuff. So I'm going to have ax squared minus 9ax plus bx minus 9b plus cx squared. And I like to collect my like terms. So notice I have two x squared terms, so I can rewrite when I combine those two terms and factor out an x squared, I have a plus c as the coefficient. And then I'll collect my x to the 1 power terms. Let's see, which one of those do I have? I've got that one right there. And then I have another x term there. So if I collect those guys by factoring out the common factor of x, the coefficient will be negative 9a plus b. And then what do I have left? Well, it looks like I just have minus 9b. That's the constant term. So now you do this equate coefficients technique. Well, what do you mean? Well, let's look at all the polynomial on the left-hand side, and 81 is a polynomial, okay? I know it doesn't seem like it. Yeah, it's a polynomial of 0 degree. The polynomial on the left has to be equal to the polynomial on the right-hand side. So let's look at x squared terms. Well, what's the coefficient for the x squared term for the polynomial on the left? You tell me.
0.
0, yeah. So 0 had better equal the coefficient for my x squared term on the right-hand side. But the coefficient of my x squared term on the right is a plus c. But wait a minute. Didn't we already get c is equal to 1? We know this to be a fact. Yes, we do. So if we substitute 1 in place of c, we get 0 is equal to a plus 1. And then solving for a by subtracting 1 from both sides, voila, I just got my a. Woohoo! So there, I just got me another unknown. Good for me. Now what? Keep going. Now it's up, now you need to get one more unknown. And you could either equate x to the 1 power terms, or if you want to be even quicker, let's equate the constants. The constant on the left-hand side polynomial is just 81. So 81 is equal to, come on, 81 is equal to the constant term on the right-hand side. But the constant term on the right-hand side is negative 9b. And then you use this to solve for b. Well, I'll just divide both sides by negative 9, and I'll get me the b, and it looks like b is going to be negative 9. So I have all three unknowns, and then what do? Now is the time for the calculus part of this whole problem. I did all the algebra, what a pain. So what I'm saying is now I'm going to integrate a over x, but what did I get for a?
I get 1.
Oh, negative 1.
Negative
So
1.
negative 1 over x plus b over x squared, so that would be negative 9 over x squared, plus c, which was 1, all over x minus 9. So this is what I have to do for integration. It's not too hard, right? So negative ln absolute value of x. This one is going to need the power rule. So it's going to be plus negative 9 times x to the negative 1 over negative 1. We'll clean that up in a minute. This one is going to be the log rule with u sub, where the u is going to be x minus 9, and du is just 1 times dx, and so we're good. This is supposed to be, I'm sorry, my computer is really wrecked today. I don't know what's going wrong with it. It's slow. No idea why. Well, it's a Microsoft Surface. That's why. It's crappy technology. Thanks, Bill Gates. Okay, and then you'll have ln absolute value of x minus 9, and of course plus c. Okay? And then clean this up because I don't like negative exponents. So your final answer to that, which it doesn't even look like I had in my notes. Oh, yeah, it does. I continued it over here. I'm going to move this ln in the front just so it looks pretty, and then I'll condense. I have ln absolute value of x minus 9. Then I also have the minus ln absolute value of x. And then this term was plus 9 over x plus c. And I'm going to do one more step. I'm going to condense these two logs into one big old log, because I can. So one big old log, when you do a difference of logs, remember the argument becomes a quotient, and I still have this term plus 9 over x, and that's plus c, and that looks like my final answer, and I'm good. Any questions on that one?
What happens to the negative sign in like before you condense it?
This negative sign right here?
Yeah.
Okay, well, there's a log property in your pre-calc or algebra class that says ln of A minus ln of B is equal to ln of A over B. Do you remember that log property from your algebra days?
I don't think I was taught that one.
Well, all I can say is I'm sorry, and if you want, we can take this offline and discuss it another time.
Okay.
Come to my office hours. But you need to know all your log properties. There's 3 of them total, Samantha. Do you know all 3?
Okay.
The answer to that is no. I'm going to be seeing you at 12 noon today, period. Okay? That goes for the rest of the class also. If you're not clear on log properties, please come to office hours and we'll just do a personal private lesson. I'll be happy to do it. I just don't have time here. Okay?
Bye.
All right. Now, what about polynomial long division? Like, check out that baby. Why do we have to do polynomial long division to that beast? I mean, the denominator does factor nicely, right? I think it factors as x plus 2, x minus 1, right? But you can't do PFD right now. Like, sorry, you can't do it. Like, don't even go, well, I'm just going to do PFD and pretend that it isn't, I don't need to bother about the improper rational function. All I can say is good luck with that. See how it works for you. It's not going to work. You're going to end up in a world of hurt. So I hope you notice that the degree of the polynomial in the numerator is a 3, which is definitely bigger than the degree in the denominator. You are not exempt. You've got to do polynomial long division first. So after you do the polynomial long division for this problem, so go watch my video, it turns out that it cleans up very nicely, and then you can go, then you can do your PFD on it and finish it up. So I do that in my video, so I encourage you to go watch the video for that one. Watch the video. It's in Canvas right now, and it's the very last video of all those 9 videos that I made for you. So have fun. So check out this baby. And yes, you're going to have one of these on the quiz, all right? Like, remember I told you, like, this is your quiz right here? This is my solution key for it. I do, like, massive solution keys. So what's next? Well, there's going to be one problem, not exactly like this one. Do your homework, but it has this flavor where it's not algebraic. So you don't, like, look at this and immediately do PFD. You first have to do a change of variables to make it look like an algebraic. Do PFD on that, and then back substitute and finish it up. What the heck did I just say? So here's the change of variables to this problem. So you're going to basically let u equal sine of x for this particular integrand. And then the derivative of sine is cos. So this is your du portion. So when I rewrite this integral, it becomes du over u minus 1. And this is a perfect candidate for partial fraction decomp. So you're going to do your partial fraction decomp, PFD for short, on this. So what do you mean? Well, here's the scratch. 1 over u minus 1, when you break it up into partial fractions, is going to be a over u plus b over u minus 1. And then you go get your basic equation by multiplying both sides by the LCD. So your basic equation is going to look like 1 is equal to a times u minus 1 plus bu. And so we'll use this basic equation to help us get the a and b, the unknowns. Okay, how about if we let u equal 0? Because that'll kill off the b term. So if I substitute u equals 0 everywhere I see an u, I'll be able to figure out what a is. Oh, lovely. Divide both sides by -1, and we have a is equal to -1. Perfect. Save that for later. And then another thing we can substitute into our basic equation here is u equals 1, and that will allow us to find what b is. Okay, beautiful. Oh, it looks like b is 1. Okay, fabulous. Now you're ready to do the calculus part. What do I mean? Well, you're going to integrate a over u, but that's -1 over u, plus b over u minus 1. Okay, fine. This is pretty easy because you're going to just use the log rule on both of these. You'll have minus ln absolute value of u plus, and in this one you can use another change of variables. I'm just going to skip it. Ln of absolute value of u minus 1 plus c. And you're not done yet. And the reason why is you need to back substitute. What was u in the first place? You got to put it back in. It was sine of x. So you'll have negative ln sine of x plus ln of absolute value sine x minus 1 plus c. Now you could do one more step. If you move this ln in front so that you're going to have a difference of logarithms and then condense this difference of logarithms into one big fat logarithm, you'll take ln of the quotient basically. So it'll have this look to it. Okay, and I think my math lab will probably take a variety of answers and give you full points. This will probably be one of the answers that'll it'll probably let you do this one also, I imagine, and it won't dock you points. I like you to condense if you can, just because knowing your log properties is super duper 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 important in mathematics. That's why if you haven't seen those in a previous class, I'm encouraging you strongly to come to today's office hours where I'll be happy to show them to you. I've taught pre-calc a million zillion times, okay? Okay, last multiple choice. What is the form of the complete partial fraction decomp of this function? We're not going to actually find the unknowns, but what would be the correct decomposition for this guy? So let's just go look at the denominator carefully before we make our choice. The denominator for this function has a repeated quadratic, okay, and then it's got a repeated linear, the x minus 1 getting squared, that's repeated linear right there, okay, and then a regular linear, a non-repeated linear, just a little linear all by himself, okay. And they're giving you all these choices here. Okay, which A, B, C, D, E, F, G, and G is none of these. Uh-oh. Does anybody want a gander a choice?
Sure.
Okay.
From the looks of it, looks like D.
D is
as
correct.
a dog.
D as in dog is correct. Why? Well, because the quadratic is always going to have the linear factor in its numerator, and then the repeated quadratic will also have a linear factor as its numerator. The repeated linears, because it's repeated twice, you get 2 of those for free, and then the last linear non-repeated just gets 1. Okay, so knowing this is important. This would be a horrible problem to figure out, because how many unknowns total do you have to go get? 1, 2, 3, 4, 5, 7. Oh God, that would take forever. That'd be terrible, but it's doable. I would probably use equate coefficients technique personally, because I love that. Okay, so I'm done with PFD, and if you still want to see more of it, you know where to go. So now let's go to one of my least favorite topics of all time, integration by tables. It's Friday, so I guess it's okay. So what are we going to do? We're going to be given a whole selection of formulas. It's from the table of integrals. And I have a book, like if we were teaching this class face-to-face, I have a really old book. It's in my office. I didn't bring it home. My dad used this. It's an actual hardback, skinny table of integrals. My dad used it when he was in college. So it's like from the 1950s. It's like real old. The pages are yellow. I would have passed it around so you could see it, hold it, look at it. But if you had a table of integrals, what you would see from it, which unfortunately teaching remote is not as good, is what I really would love for you to see is that it's grouped in categories. It isn't just a list of thousands of formulas. It is a list of thousands of formulas, but they're done in categories where you can go to, as long as you go to the right category, you don't have to read the whole darn book, which would be really dumb. So the benefit is once you are looking at the correct category, it shouldn't be too hard to look through that category's listing of formulas and get to the right thing. So that's sort of the trick, is getting to the right category. Now my math lab doesn't really give you the feel for that. They just give you, they already pick the category for you and then they show you, well, sometimes they give you a list, but it's not the same. So why do you care? Because if you get an integral that isn't integrable using all the techniques that I've taught you now, by the way, I'm done teaching you techniques. So you are now blessed. Congratulations. I am blessing and validating all of you in the class. You now have all of my tricks. You know all of my tricks on how to integrate. There's no other tricks out there. You know them. Congratulations. Now, are you experts? No. That's why you need to practice. You get good at all these integration techniques that we went over, and there's a lot of them. You know, multiplying by special version of 1, integration by parts, trig powers, trig substitution, partial fraction decomp, the split up trick, all these different ways that you are to know how to integrate. Sometimes those all fail you. So when those all fail, after you get done crying lots of tears, then you hope that an integration table or a table of integrals will help you. Okay, so the motivation for this table lookup section is just because you're really smart now and you know all these fancy schmancy integration techniques, that those still may not save you for really nasty integrals. So you go look up these formulas that have been done by computers, okay? So, and then I got some more bad news. Sometimes even the tables are not a cure-all. Sometimes those don't work either. Like, now what? Well, now you just go into a fetal position and cry your heart out. No, you hope a computer can go help you. Okay. So if you do have a hard copy of the book, there's an appendix in the back of the book that has an abridged version of the table of integrals. It's not a very good one. It's very shortened, but it's good enough for government work. So you can use that. And did I mention that Briggs sucks yet? Not today, but Briggs sucks. What I don't like about Briggs is the same reason I don't like about Briggs when we were doing inverse trig functions, is that Briggs does not give you the general rule for a lot of these formulas. In other words, I like U. I like to see U's when I see one of these table of integrals with the formulas, and Briggs likes X's, which is terrible because the U's are more general. So this is an example of something you might see in the table of integrals. So if your integral has this flavor to it or this pattern to it, and you can identify the u, the du, and whatever those coefficients are, a and b, then you don't really have to do much work. Just plug it into the formula and you're done. Isn't that cool? But getting to the formula is the hard part. Picking the right one. Here's another weird formula. Check out this baby. By the way, this formula would not be a trig sub candidate. Why not? Even though it has a radical in it. Why? From what I taught you about trig sub, I'll check the chat box. Does anybody want to try their hand at this? Why would this formula or an integral that had this look to it. I'll just make something up. Like let's say I had an integral of a square root of 2 plus 9x all over x dx, which has this pattern. Why would you not want to use trig sub, or trig sub does not apply? I'll wait. Okay, so they're claiming that you could use integration by parts on this and it would work. Okay, but just plugging in the formula would be really nice. And then this one, you can use multiplication by special version of 1. I taught you that one already, but they have a formula for it anyways. Okay, now if you do have a hard copy of the book and you do look at the appendix in the back of the book, you're going to see different classifications. So one of the classifications, a whole list of them, come with u to the n. Here's another classification. Sum or difference of squares. A sum or difference of squares underneath a radical. Another difference of squares. They have one just for trig functions. Another category just for exponentials. All sorts of different categories. So they're grouped out, which makes it easier to navigate through this big yucky table. Okay, so let's start with a MyMathLab problem that I picked out for you. Similar to MyMathLab problem, although Briggs doesn't use U's. Briggs has X's. Okay, look at this guy. That is definitely not a trig sub candidate because you don't have a sum or a difference of squares under the radical. Okay, you could use change of variables on this and then possibly partial fraction decomp, but it might be nicer if we just figure out which one of the formulas. So they're giving you a hint. Because the radical underneath, what's under the radical is a linear function, x minus 1 is a linear function, consider forms that have that flavor to it. So look in this big old list of, choices. Does anybody have that look to it that has this flavor to it? If you can't pick the right formula among all the choices, you won't do so well on these problems, okay? Now this stuff isn't going to be on this week's quiz because this week's quiz only has trig sub and partial fraction decomp, but this crap will be on the quiz in the following week. So does anybody want to guess here about which one of these puppies applies?
49.
57?
No.
49.
No. Okay.
55.
I claim all the ones that I'm crossing out. Why am I crossing out all these ones here with 47, 48, 49? I'm crossing all those out because none of those have a radical in it. And my original integral has a radical in it. So I need to choose something that's got a radical, and the radical has to be downstairs in the denominator. Somebody said 57, and whoever said that, I think you might be right. This one is correct. So how come? Well, because the denominator has a radical in it, yay, and the u is going to be our x, of course. And our original integral also has an x sitting out in front of the radical in the denominator. So this one has all of the components needed, but we have to figure out who the u is, who the du, and who the a and b are. Now, a plus bu, which they have underneath the radical, if we rewrite this as bu plus a, so it looks more like our radical, then I hope you can see that our radical, to make it match, looks like 1 times x, where u is going to be the x, plus a negative 1. Does everybody see that's going to be what our radicand is? So in other words, when we use this formula, u will be x for us, du is just 1 dx, okay, that's nice. A is negative 1, and b is the coefficient on u, which is for us a 1. So these are all the things that we need to distinguish before we actually use the formula. So notice there's two versions of the formula, and you have to pick which one. Sometimes this gets a little complicated. So which one do we pick? Is the A that we're going to pick for A a positive number, or is our A a negative number? Hello?
Negative.
It's
Negative
negative.
number.
Ooh, so we better pick this formula and not the one above it. Ha 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 ha. Ooh, that would have been really bad. So we'll pick the bottom one, and now let's plug in all our junk. So we're going to have 2 over the square root of negative A, but our A is -1, so negative -1 is a positive one, times arctan of the square root of A plus BU. For us, that's -1 plus 1 times X, all over negative A, but that's negative -1 for us, and then plus C. And then clean this mess up, because this is really just going to be 2, and this is arctan, and dividing by 1 doesn't really do anything. You know, it's just like, yeah, okay, dividing by 1. And so we're going to just have the radical square root of -1 plus X, and then, of course, plus C. And we're done. So we just did an integration using a table of integrals. And so the trick is you got to pick one of the formulas that's the closest match to your original formula. So if it has a radical, the formula had better have a radical in the right spot, and so on. Okay? Questions?
Yes. So how did you choose the A again? Looking at it.
Okay, so when you look at the radical that we have, Kobe, do you see it's square root of X minus 1?
Yeah.
And do you see that the formula that they have there is the square root of A plus BU? I need to make these two match. That's your job,
yeah.
not mine.
I
That's
see.
your job.
So you
if
just switched it?
Yeah, I kind of rewrote it as -1 plus X, which is the same, right?
Mm-hmm.
And then this is really 1 times X. And then my A is the pure number sitting all by himself. So my A for my problem will be a -1. And then the B is the coefficient on your U, where U has to have a variable in it. But for us, the U is just X.
Yep.
So our B is just going to be a 1. And then our A will be -1. Does that help?
Yeah.
Okay.
Thank you.
And when you find the match, you got to be careful, because sometimes, you know, you might have a negative or whatever. It gets kind of weird. Okay, check out this baby. Now, it says using trig substitution, but no, we're going to not. I claim you actually could use trig sub here, but we're not gonna, because we're going to use the table of integrals instead. So using a table of integrals, in this case, a formula sheet. Okay, so notice that the expression inside the radical is a difference of squares. So if I rewrote this, oops, as, sorry, ooh, my eraser's not working. The integral of x times the square root of x squared squared minus 3 squared dx. That might be a little helpful to make sure we pick the right formula. Okay. Look at all these formulas. Yeesh, which one is it? Oh my God, some people are saying 40. Is that the one? I don't know. I don't have it in my notes. I got something else in my notes. I don't even know what the heck I'm doing here. Does 40 look like it would be it?
Kind of say it does.
Well, here's the problem. I know why you want to say 40, because you've got something sitting out inside of the radical, but this is u squared. So if we start by saying our u will be x squared, isn't du 2x dx? And then this is not u or u squared for our choice of u. So I claim 40 is not the correct choice. Sorry. I know you're not going to like this. It seems like it should be easy.
41. I'm sorry.
No,
Totally.
because there's nothing in our denominator. We don't even have a denominator to do business with. So it can't be 41 because ours doesn't have the flavor.
43?
No, it can't be 43 either because once again, 43 has the radical in the denominator and we don't have even a denominator to do business with. Stop picking things that have denominators in them.
So basically 39 would be our only
Yes,
other option.
thank you. It's going to be 39. Gosh, thank you. Why?
Because
Does it have a radical or denominator?
Squared.
yeah, x
Yeah, first
squared
of all,
would be
there's no
u.
radicals in the dang denominator and there's no denominators. But does it work for us? Yes, because I just said we're going to let u be x squared for our purposes. So it does look like we're having a u squared there minus a squared. Who's going to be our a for our problem? 3, good choice. And then the du is 2x dx, and we have part of our du already in the integrand. That's why that x is there. It's not part of the formula. It's part of the du that's going to get used up for our choice of use. The only thing that we wish we had in this integral in order to continue using the formula that we chose, which is indeed number 39, you're going to need to put a 2 in there provided you divide it out. So now this formula does indeed have the look of 39, where the 2x dx comprise the du portion of formula 39. Okay, and so now you're ready to apply this huge formula. So let's do it. What's u over 2? Well, remember, our u is x squared. So it's going to go x squared over 2 times the square root of u squared minus a squared. That's x to the 4th minus 9 for us. Minus a squared, that's 3 squared over 2, times ln of the absolute value of u, but that u for us is x squared, plus the radical again, which is sort of this original radical, u squared minus a squared, and then of course plus c. And then you can replace the 3 squared with 9.
Do we have to add the 1/2 at the end? Multiply everything by half? Or not?
Well, the 1/2 is, oh yeah, thank you. This 1/2 is what I hear you talking about. Yes, thank you. But don't multiply the c by the 1/2. Thank you. Almost forgot my 1/2. And then you can distribute this 1/2 and make it look pretty. So your final answer will be x squared over 4, square root of the x to the 4th minus 9 minus 9/4 ln absolute value of x squared plus the square root of x to the 4th minus 9, and then plus c. Okay, that's another table of integrals for you. This is a pain in the butt, and I'm not done. I told you this was my least favorite. Because if you pick the wrong formula, you just go down the tubes. And I can't on a quiz or an exam go, well, you picked sort of the right formula. I'll sort of give you partial credit. It's kind of hard. So let's look at another one. You get better by practice, okay? That's how you do it. Look at this mess. This is tricky because it's got trig in it, and yet we're not going to use any formulas that involve trig because you're going to do a substitution kind of like I did for that PFD problem. You're going to go, hey, let u be cosine x, and then the derivative of cosine is minus sine. But wait a minute, we got a problem here. We're going to have to use a trig identity on sine of 2x. Does anybody remember the trig identity? It's called the double angle formula. What's sine 2x the same as?
2 sine of x times cosine of x.
Good. So if I replace that numerator with 2 sine x cosine x, and then use these choices for u and du, then when I rewrite this integral, it's going to look like 2, and then I wish there were a negative, so I'll kind of put a negative in there, negative sine x, and I'll put a negative out front, cosine x, and then I'll still have the 2 plus cosine x downstairs. Sorry, this is getting to be kind of a mess. And then this is going to look like, I'll pull the 2 out, the minus sine x is a du, that's your du, and cosine x is your u, so you'll have u du in the numerator, all over 2 plus u in the denominator. Okay? So now the question is, do any of these formulas look like that? And I'll give you a hint. Any of the formulas that have a radical in it here, do not even touch those with a 9-foot pole, because that is not what our guy looks like. Okay. And whoever says is saying 47 in the chat box, all you folks, that would be Anaya, Lisa, and Jose. You are correct. Thank you. So 47 is the correct choice. It's got the flavor. And we know what u is. It's cosine. And we know what du is. It's negative sine x dx. But who's A and who's B for our guy? A is?
2.
And B is?
1.
1. Very good. And now you're ready to put it all together. So, but we also had that negative that we had to stick in front, just like the previous problem, we had that half. So negative, whatever that formula they're going to tell us, and then we'll distribute the negative at the very end. So they're telling us, if you look here, 1 over b squared. Well, that's not very interesting. 1 over 1 squared. Okay, fine. Then what?
2 plus u.
Parentheses a, which is 2 plus bu, that's just 1 times cos, minus a, that's 2 again, ln, absolute value of a plus b times u, but that's just cosine x. And I think that's it. Yeah? And you can then distribute your negative here, and this is just 1, so you can clean it up, and you'll get negative 2 minus a cos, and then minus a minus is a plus, 2 ln, absolute value of 2 plus cosine x plus c. Okay. Woo! That kind of sucked, but okay. I think that'll work. Okay, we're getting kind of low on time, but for example 4, if you look above for a formula here, which one of the formulas, or are there any, that would work? I claim one of the formulas above here is a choice. So look at all these formulas here. Does anything match example 4? Notice you've got an x here, and you've got an x underneath the radical, and the radical
55.
is
55.
55, I think, is correct. Yeah, 55, good. And who's your u and your a and your b?
The B is 5.
5.
Okay, b is, I claim b is negative 5. Be careful. You see why?
Yeah.
See a plus there? So if you rewrote ours as 3 plus negative 5x, which you need to do, then your b is going to be a negative number. This is key. And then what's your a?
3.
And then who's your u?
X.
Yes.
X.
And then what's du? If u is x, what's your du?
Dx.
Okay,
Dx.
so you're good. And then I think you can just plug into that formula for 55, and don't forget this 2 here. I would pull out the half. So whatever your formula you end up getting, don't forget to multiply it by that half, and then don't forget to do a plus c. Okay. All right, I'm going to do reduction formulas now. We're on to reduction formulas. What the heck is a reduction formula, and why do you care? I claim you already know how to do this because I kind of already taught you this, but you may not agree. So let me remind you about something and why I claim you kind of already know how to do this. Do you guys remember when we did integration by parts? And the whole thing was, okay, u dv is equal to uv minus the integral of v du. Remember this? Say yes.
Yeah.
Yes.
And then this integral was supposed to be integrable, right? Okay, so this actually kind of has a flavor of a reduction formula. It has the flavor. What do you mean? Well, your original integral is not integrable. It's like, I can't do it. Ugh. But the new formula is something times something minus another integral. Okay, and that's kind of the flavor of a reduction formula. And then you just hope that this integral is integrable. And if it's not, then you use some other technique on that. And we've done something like that where we actually had to use repeated integration by parts. Remember that? On this integral? And so that could happen too. It could get nasty where you have to rinse, repeat, and keep going. And that's sort of the flavor of reduction formulas. And so know how to do that. So it's kind of cool, but not hard. So if any of the formulas in your table, or when you're on My Math Lab and they give you a whole truckload of formulas, it's like, which one of these do I pick? Some of those formulas might actually be kind of weird, and that they have an integral on the right-hand side that you have to kind of keep going. And you're like, oh, man. And then you might have to pick a new formula from the selection of formulas so that you can keep going. So I have a really cool example that I have here in my lecture notes that's going to sort of take us down that path. So are you ready? This is reduction formulas in action, people. Here we go. It's not that hard because you kind of have already done this. You already have the experience. So check this baby out. X cubed sine of x is what we have to integrate. I actually claim that you don't need no stinking formulas. That can be done by repeated integration by parts. Everybody in this room could do it. I already taught you how to do it. But using formulas from a table is a little quicker than having to do it by hand. So let's do the formulas from the table. And there's only 3 formulas to pick. So out of these 3 formulas, which one matches this the best?
The second one.
Second.
Very good. Why did you say that?
Because u is cubed.
Mm-hmm. And then you have a sign in there, right? So we'll use this formula first. We'll call it number 2. So we're going to use that first. So when we use this formula, we have to identify some things. Who's the u? And of course, anytime you identify u, you want a du. And then what's the n? What's the n, that little power for us? Okay, so let's get these 3 ingredients, and then we'll use this big old formula over here, okay, which is known as a reduction formula. Okay, why is it a reduction formula? Because the formula itself has another integral in it that we're going to have to go do. So what's our u? It's easy, just pick it.
X.
Good. And then du is?
Yep.
Yep. And then who's n for us?
3.
Good. Okay, so when we use the formula, our original integral is going to become a negative u to the n, so that's negative x cubed cosine of u, so cosine of x, plus n, that's a 3, times the integral of u, but that's x, to the n minus 1 power. What's that going to be?
Square.
Squared.
Squared, good. Times cosine of u, cosine of x, du, but that's dx. Okay, so I used the reduction formula. Now what? I'm not done. Because do you see I have another integral that I now have to go do? And by the way, you could use repeated integration by parts on that. But we'll use a formula instead. So which of the formulas that I have supplied here, and there's 3 choices here, do I need to use on this integral?
Third one.
Very good, the third one. Why? Because it looks like u to the n cosine of u. Let's pick the u, the du, and the n this time. So what's u? It's still what?
X.
Yep, du is still,
dx.
and n is different now. It is
2.
a 2. Okay, So I'm going to keep copying down, you know, the parts of our answer that are still there. We still have that first term, negative x cubed cosine x plus 3 times some junk. And I'm going to put brackets here because when we use this reduction formula, it tells us to do u to the n sine u. So for us, that'll be x to the 2 power sine x minus n, but that's 2, times the integral of u to the n minus 1, that's x to the 2 minus 1, which is just 1 power, times sine of u, that's sine of x, dx. Oh man, I got another integral I got to go do. Oh, bummer. And by the way, before I get too far afield, let's distribute that 3 because that's dangerous, not taking care of all these coefficients that are going to be messed up if we don't deal with it early. Okay, so I've got one more integral I'm responsible for before I finish up this problem. Does this integral match any of the formulas I've supplied for you here in these choices?
The first one.
Yeah, the one we haven't used yet. Very good. So we're going to use formula 1 on that, where u is x, and then du is still dx, and there's no n in that formula. So we're still going to have to multiply the 6 with that guy. So you're going to have sine of x minus u cosine u, that's x cosine x, and of course plus c. So our final answer, so I don't have to rewrite stuff, is going to be this huge expression, negative x cubed cosine x plus 3x squared sine x minus, and you might want to do yourself a favor and distribute that negative 6 so it looks prettier, but negative 6 sine x and then negative 6 times negative x cos is positive 6x cos x plus c. Woo! And that is reduction formulas in action. Yep. So, Javier, why do you say you're getting Math 130 flashbacks? They don't do any integration in Math 130, do they? I don't think so. It's more like you're kind of in a loop. Yeah, you are in a loop, that's for sure. Yep, it is kind of like you're doing loops. You keep looping until you don't. Okay. So the last little thing that I want to look at here, which one of these do I want to look at? We could do this one, but I don't feel like up to it. I'll just tell you that, I supplied, this is the formula you're going to use. So go use this formula, and you're going to have to use this formula repeatedly until you're done. Okay, so you have to use the same formula over and over where the n keeps going down by 1. So it keeps decrementing until you finish it out. So that's kind of nice. I'd rather look at example 7 because example 7 has us completing the square. So you can see that sometimes you can't use a formula until you get your integrand to match. And you may have to do some algebra in order to get it to match. And this is an example that I haven't taught Math 122 in a while, but Math 122 is calculus for poets. It's like second semester calculus for poets. It's a lot of biology students take Math 122 instead of 121 and 122 instead of 250 and 251. But this is one of the problems I put on their exam because they learn integration by tables also. So here you go. How do you do it? Well, I wouldn't even try picking one of these formulas yet because it doesn't have that look yet. You have to first complete the square. So well, what do you mean? Yeah, you need to complete the square on the expression that's inside the parentheses in order to get it to look like either a sum or difference of squares. So let's do the scratch first. So the scratch is, take a look at x squared minus 6x plus 10. Okay, what? Well, if I'm going to try to complete the square for this expression, I need to add and subtract a magical mystery number in the same sentence. And the magical mystery number is always the middle coefficient divided by 2 squared. So what's negative 6 over 2 squared?
9.
So you're going to go x squared minus 6x plus 9 plus 10 minus 9. Okay, and then this right here is supposed to be a perfect square trinomial. That's why you did all this work. It's supposed to factor as something squared. How?
Minus 3.
And then this is just plus 1, but you could write that as something squared. 1 squared. Now, I claim that our integral, if I rewrite it equivalently, it's going to look like this sum of squares getting squared. Interesting. Interesting. So look at all your choices and tell me if any of those puppies has the look of a sum of squares getting squared. In the denominator, of course.
A.
F, I think F.
F is correct. Why?
Because it's a sum of squares to the power of n.
It's going to be our choice where n is going to be the squared. And n will be 2 for us. Now I want to say something about this formula because this is very common when you're looking at a table of integrals. A lot of times you'll see a plus or minus there, which is nice because it gives you a choice of plus or minus. But you can't just put plus or minus in your final answer. That's wrong. Well, they have it in their answer. Yeah, but you have to make a decision. You have to pick one. So you have to, since our original problem has ooh, what just happened there? I don't know. Since our original problem has a plus in there, right there, I'm just putting, overloading the plus, we have to pick the plus only. So in other words, everywhere you see a plus or minus in their answers, you have to pick the plus only. Don't be putting pluses and minuses. Now, if our original had had a difference of squares, which it isn't, then we would have put minuses everywhere. I do want to say one more thing. This is more for people that are really into subtleties and details. I'm talking to you people. You know who you are. I love you. A lot of times when you see a plus or minus in the original, sometimes in the answer, you'll see a minus over a plus, which means you'll have to flip it. Like it'll mean like if the original had a plus, in your answer, the pluses will have to get replaced with a minus because this thing got kind of flipped over. But that's not the case with this particular formula, the plus or minus. We also just have pluses or minuses in the answer. So for us, the u is going to be the x minus 3. du is just 1 dx. And a for us is 1 because we had the 1 squared. So, and then the n is a 2. So we have all of these mapped out. Now we can use this huge reduction formula. So if I use it correctly, oh my goodness, this is going to become 1 over 2 times a squared. Why do I have... Never mind. 1 over 2 times a squared, that's 1 squared. And then I have times n minus 1, but that's 2 minus 1. Times this whole thing. So I'm going to have u, but u is x minus 3 all over the quantity a squared plus u squared to the n minus 1. So n minus 1 for us will be 1. And this is going to be 1 plus the x minus 3 squared. Plus, and now we have 2n minus 3. So 2 times n, which is 2, minus 3, times another integral. Oh man, I'm running out of room here. Oh, good God. And this new integral is going to be 1 over the, so what's it going to be? We have a dx here. it's going to be a squared plus, because we have a plus, 1 plus x minus 3 squared. Okay. And we have that. And we're almost done. This just looks like it's 1/2. Okay, this is just 1/2. So I'm going to distribute it. So you'll have 1/2 times this first term, which is x minus 3 all over 1 plus x minus 3, the quantity squared, plus, and then 2 times 2 minus 3, that's just a 1. How do I integrate this? Does anybody want to tell me how they'll integrate this? I claim you know how to do it. You don't need no stinking integration formula. Any guesses?
Maybe arctan rule?
Fantastic! Yes! Arctan rule, where u is x minus 3. du is just dx, and a is 1. Beautiful. So it's just going to be 1 over a, that's 1 over 1, which is like nothing, just a 1. And then arctan of x minus 3 over 1, that's just x minus 3 there. And then this whole thing plus c. And I'm done. And I'm done with today's lecture. Congratulations. You now have seen integrating using tables, which, to recap, you have to be very good at choosing the formula that matches your integral. And sometimes you might even have to do some algebra on it in order for you to pick the right formula to use. So it can be a little bit of a pain in the butt. It's not just a cakewalk on picking the right formula to use. You still got to work it. And sometimes integration tables don't work either. You can get doubly screwed. Okay, I'm done. Happy Friday. If you are done, you can leave. I'll stick around for any last minute questions. And remember, I have office hours today from noon to 2. You're welcome to come. And good luck on quiz 5 this weekend. Bye.